Okay, we're here in Chapter 7 to talk about gases, liquids, and solids. And actually, mostly what we'll be talking about here is gases and liquids for the most part. So to start out, let's just review. Gases, remember, are one of our phases of matter. Liquids and solids, obviously, were the other two. And how we told them apart way back in Chapter 1 was the fact that gases had undefined shape and undefined volume, which meant that gases could expand and contract. And we know we have practical experience of this because you put pressurized air in your car tire, or when you open a pop can and you hear that psh sound of the gas escaping. It's because it was pressurized and then you're opening it to the atmosphere. There's a large distance separating your particles versus the particles in a liquid or the particles in a solid, which is one of the reasons that gases can expand and contract so much, because there's such a large distance between things. When we talk about gases, because of the fact that the volume is undefined, unlike liquids, we need an additional characteristic, an additional variable to define them. And so with gases, we talk about pressure. And pressure is defined as force over area. And practical application here is if you've ever worn a pair of stiletto heels versus a flat, there's a different amount of area, right? So if we were to draw what your foot looks like in a stiletto heel, you have a little tiny place where your toes are, and then you have the heel versus the flat, where you have lots of surface area contact between your foot and the floor. So in the stiletto example, very small area means that the pressure that you feel, if this is a really small number, then this has to be a pretty large number. So the pressure on your foot is quite large. Versus for a flat, you have lots of area here. And so the area then in this term is a bigger number, which makes pressure, relatively speaking, smaller. In chemistry, when we talk about pressure, we talk about it in terms of a particular set of units. So most commonly what you'll run into here in Chemistry 121 is atmospheres. Or if you were putting pressure of gas into your car tire, you would have PSI, or pounds per square inch. There are also torr, millimeters of mercury, and pascals. For a chemist, pressure is caused by the collisions of particles with the sides of their container. So we know that particles are always in random motion because we know that anything that has temperature, anything above absolute 0 Kelvin, is in motion. So even solids that you're looking at, their molecules are actually jiggling back and forth, as long as we're at a temperature above 0 K. So there are collisions then between the particle and the container, which result in the particle feeling a force. So if you think about it, excuse me, fighting a cold here. If you think about it, the particle smacks into the side of the container, which then feels some force. Kind of looks like this. You've got particles in random motion, jiggle, jiggle all over the place, and they're running into the sides of the container. So out of this, we need to have some mathematical models that will help us to predict how gases will behave. And first of all, let's talk about the relationship between pressure and volume. Let's consider the two cylinders in the next slide. Which do you think has the higher pressure, and why? So take a moment, hit pause, think about that. Okay, so when we're looking at cylinder A, we see that it has a really large volume, right? My volume's from there to there. Versus in B, I have a smaller volume. Now notice, I have approximately the same number of particles in both A and B. And I didn't say that we were considering temperature in this, so we're going to assume that the temperatures are the same. Plus, they're sitting side by side, so it's likely that their temperatures are the same. So when we look at this, we can see the greater volume means the particles have more area to collide with. The smaller volume means we're squishing those particles down, and so they're colliding more often with the sides of the container. So as the volume gets smaller, the number of collisions between the particles in the container goes up, which means that pressure goes up. So the container with the smaller volume has the higher pressure. Gases with the same temperature and the same number of particles will have higher pressures and smaller volumes. So this comes down to the fact they have less area to collide with, more collisions between the particles of the gas in the container, gives you a higher pressure. Which means volume and pressure are inversely proportional. And what that looks like is P is proportional to 1 over V. What about pressure and temperature? We know that temperature is a measure of how fast molecules are moving. So if you have a really high temperature, things are really hot, it actually means that molecules and particles are moving really fast. Versus a really cold temperature, particles are slowing down. They're not moving as fast. So if pressure is related to the number of times that the particles are colliding with the container, and temperature is telling us how fast they are going, how do you think they're related? Well, faster movement means more collisions with the container, which means a higher pressure. Slower movement, or a lower temperature, means fewer collisions with the container, which means a lower pressure. So therefore, P and T are directly proportional. So P is proportional to T. What about pressure and the number of moles? And the number of moles is going to be expressed when we talk about gases as the variable lowercase n. So if you think about it, I'll give you a moment to think. Okay, so what do you think? If the number of moles goes up, then the amount of things that are colliding with the sides of the container goes up as well, which means that the pressure goes up. So they are directly proportional. So increase in the number of moles makes an increase in the number of particles. More particles means more collisions, and more collisions means an increase in pressure. If you put all of this together, you get what's called the ideal gas law. And it's written as PV equals nRT, right here, where that uppercase R is referring to a gas constant of 0.0821 atmospheres times liters divided by moles times Kelvin. So a really long unit there that goes with this number. It's a model of gases that works well most of the time. That's why it's called the ideal gas law, not the all gas law. Your temperature always has to be in Kelvin, and the units of temperature, pressure, the number of moles, and volume must always match R's units. So if R, like we saw up here, is in atmospheres, liters, moles, and Kelvin, then your volume has to be in liters, and your pressure has to be in atmospheres. So let's do some examples with this. The volume of a sample of nitrogen gas at 1 atm and 25 degrees Celsius is 5.0 liters. If the flask is emptied when the nitrogen is used in a reaction to make ammonia, how many grams of nitrogen were in the flask? So with the ideal gas law, we have pretty much two different types of problems that we'll generally see in these gas law problems. One type of problem is the example that we're looking at here, where I've got some gas and it's engaging in a chemical reaction to produce something. And what I'm asked about in the problem has to do with either something that's produced or something the gas is reacting with. So this is one type of problem where we've got a chemical reaction occurring. And hopefully what you're realizing is, whoa, if we have a chemical reaction occurring, then it's probably a good idea to write out and balance the chemical reaction. So let's go back there. So we have nitrogen. Tells me I have nitrogen here. Oh, my highlighter's not working. And it's at 1 atm. Apparently, we're not going to work. And the nitrogen is used in a reaction to make ammonia. Now, this question is missing a key piece of information, which I would give to you on a quiz, which is what the heck is the other reactant, which is hydrogen gas. So remember, nitrogen and hydrogen are both one of the silly seven. So when they show up by themselves, they show up as diatomic molecules. So I have nitrogen plus hydrogen going to ammonia, as I was told in the problem, and then I have to balance the reaction. And I need 2 ammonias and 3 hydrogens, and then everybody should be happy. So the information that I've given is all for nitrogen. I'm told that the pressure equals 1 atm and that the temperature equals 25 degrees Celsius and the volume equals 5.0 liters. Which, if we think about the ideal gas law, PV equals nRT. I know P, I know T, I know V. R is a constant. So the only thing I'm missing here is the number of moles, which, given that I want to find out about ammonia, and we know that if I know the number of moles of nitrogen, I can use my coefficients to figure out the number of moles of ammonia, then it kind of makes sense that my approach here is to take my variables and solve for the number of moles. So I'll put in I'm going to solve my algebra equation first for N. So N will equal PV over RT. Pressure is 1 atm. We can use that unit because we know that R is in units of atm. R is also in units of liters, so my volume is set to with the 5.0. But temperature has to be in Kelvin. And remember from chapter 1, or maybe it was chapter 2, to change from Celsius to Kelvin, we have to add 273 degrees. So this becomes 298 Kelvin. And if you don't remember this conversion of Celsius to Kelvin, remember that it is on your blue sheet and you are responsible for knowing it. So then over here, I've got my 0.0821 liters times atmospheres divided by moles times Kelvin. There's R. And then my temperature is 298. Okay. And then I just have to put it into my calculator. So 5 divided by 0.0821 divided by 298 gives me the number of moles of nitrogen as 0.204. And actually, yeah, that's probably a good number of significant figures. But the problem didn't ask me about nitrogen, it asked me about ammonia. And remember, we said, hey, with our balanced chemical reaction, we can use our mole-to-mole ratio given in the reaction to go from moles of nitrogen to moles of ammonia. And since there's 2 moles of ammonia to every 1 mole of nitrogen, then I can take my 0.204 moles of N2 and multiply by those coefficients. 1 mole of N2 equals 2 moles of NH3. Remember, this is a concept that we learned in chapter 6. And then finally, my last step, the question asked me for grams of ammonia. So I need to use the molar mass of ammonia. 1 mole of ammonia is 17.03 grams. And then into the calculator it goes. And I get 6.948, which I only need 2 sig figs. So this becomes 6.9 grams NH3. Let's try another example. So remember I said there's 2 general ways that ideal gas law problems will be asked. We just did an example where we looked at a sample of a gas that was used in a chemical reaction. And we were given information about the gas and then asked about something else that was occurring in the reaction. The second type of ideal gas law problem that you would see is here in example number 2. And generally what happens in this second type is I have a sample of gas and I change something about it, either the temperature or the pressure or the volume, but a chemical reaction does not occur. So I won't have any chemical reactions occurring. I'm just taking a sample of gas, and changing its pressure, temperature, or volume, and finding out something new about it. So let's read the problem. It says a sample of gas has a pressure of 345 torr at negative 15 degrees Celsius and a volume of 3.48 liters. If the temperature rises to 36 degrees Celsius and the pressure to 468 torr, what is the new volume of the sample? So with these types of problems, you're given lots of information, and it's a good idea to sort it out into what's happening, what the sample of gas started at as conditions number 1, and then what the new conditions are, so conditions number 2, after those changes have been made. So to do that, I'm going to list out P1, P2, V1, V2, T1, T2. And then we can also talk about N1 and N2. But since there's no chemical reaction occurring, what should be true about N1 and N2? Well, if no reaction occurs, then the number of moles must stay constant. So that means that N1 equals N2, which will have some consequences for how we approach this problem later. So we have a sample of gas. It has a pressure of 345 torr at negative 15 degrees Celsius and a volume of 3.48. All of those pieces of information are the gas initially. So those are all my ones. So 345 torr. Volume is 3.48 liters. And the temperature is negative 15 degrees Celsius. Then, if the temperature rises to 36 degrees Celsius and the pressure to 468 torr, what is the new volume of the sample? So now we have a new set of conditions on the same gas. The pressure is 468 torr. The volume, we don't know. We've been asked to find. And the new temperature is 36 degrees Celsius. So when faced with these types of problems, where you have one set of conditions and then another set of conditions, it's a nifty trick to write out two ideal gas laws. So P1 V1 equals N1 R T1, and ratio it to a second ideal gas law for the second set of conditions. P2 V2 equals N2 R T2. And this technique will work on any of these types of problems. Your book sorts this out into specific laws, Charles's law, Boyle's law, the combined gas law. And if you want to memorize each of those individually, you certainly can. But this technique will allow you to derive them whenever you need them. So my first step is I've listed all the information out, then I've written these two equations, and now I just need to cross out what stays constant. So we talked about the fact that because no chemical reaction occurs here, the number of moles stays constant. So that means N1 and N2 cancel each other out. R, by definition, is a constant, so it cancels out as well. Everybody else is in there because it changes. So that leaves me with P1 V1 equals T1 over P2 V2 equals T2. Now, the question asked me for the new volume of the sample. So what I need to solve for is V2. Let me rewrite this. I think I have a solutions page on the next page. Yeah. So P1 V1 equals T1 over T2 P2 V2. I need to solve for V2. And you can do this using whatever algebra plan you have. If you're not familiar, you might try cross-multiplying both sides, because we need to get that V2 out of the denominator. So once I cross-multiply, I have T1 P2 V2 equals P1 V1 T2. And if I want to isolate V2, that means I want to get it by itself, then I need to divide out what's with it, the T1 and the P2. So these guys will cancel. So I'm left with V2 equals P1 V1 T2 over T1 P2. And now it's just a matter of plugging things back in. So let's go back and find out what that was. So P1 was 345 torr. Notice I don't end up with having R in my equation, so I can actually leave the pressure in the units that it is, as long as it's consistent. So I see that P1 is 345 torr and P2 is 468 torr, and since they're both the same unit, I can leave them where they are. Volume works the same. I have 3.48 liters. We don't know the new sample, and it doesn't specify what volume unit I need, so I'm just going to leave it in liters. Temperature, on the other hand, I have to change to Kelvin. I don't have a choice about this. So my, let's see, I need to rewrite all this. So P1 was 348, and P2 is 468, and V1 was 3.68, and we don't know V2, and T1, T2, T1 was negative 15, and T2 was 36. So I need to change my Celsius to Kelvin by adding 273. So 273 minus 15 gives me 258 Kelvin. And 36 plus 273 gives me 309 Kelvin. And now I'm ready to just plug everything in. So P1 was 348 torr. V1 was 3.68 liters. T2, excuse me, like I said, I'm fighting a cold. I shouldn't say I'm fighting it, I have a cold. And then T1 is 258 Kelvin. And P2 is 468 torr. Okay, so 348 times 3.68 times 309 divided by 258 divided by 468. I get 3.277, and I need 3 sig figs in my answer, so 3.28 liters. All right. With gases, what we've been talking about so far is treating gases when they are alone, when they're just one type of gas. But if you think about it, the practical application of gas laws, at least for lots of those of you who want to be nurses and dental hygienists, is things like the air we breathe. And that's actually a mixture. And the amount of gases that are dissolved in your blood, that's a mixture as well. And so what comes into play for us here is something called Dalton's law of partial pressures. And this law looks at the fact that when you have a mixture of gases with individual pressures, P1 and P2, that the total pressure of the system just equals the sum of those individual pressures. So let's go ahead and look at number 38 in your textbook for an example. Number 38. Okay, so number 38 says a gas mixture contains helium, neon, and H2S at partial pressures of 125, 175, and 225 millimeters of mercury respectively. If all of the H2S is removed from the mixture, what will be the partial pressure in millimeters of mercury of neon? So go ahead and think about this for a moment. Okay, so you've got hydrogen, neon, and H2S. They're 125, 175, and 225 millimeters of mercury. Okay, so when you look at this, we've got 125, 175, and 225. If all the H2S is removed from the mixture, the partial pressure of neon will still be the same because neon had a partial pressure of 175 to begin with. And taking away the mercury does not change how much neon there is, which is giving you that partial pressure. So the answer is 175 millimeters of mercury, which we didn't really need to do. So I didn't need to have a solution slide for, I guess. So liquids. Liquids have undefined shape and defined volume. They do things like evaporate, change from a liquid to a gas. They boil, also changing from a liquid to gas, freeze, etc. When these processes happen, does energy enter or leave the liquid in each? Well, if you think about it, boiling is kind of a straightforward one to think about. In order to boil something, you have to put energy into the system, into the liquid in the form of heat in order to get it to boil. So energy is entering the system. On the other hand, when you freeze something, you are taking energy away. You are removing it by placing it in a colder environment. So when we talk about energy leaving or coming into a system, we use the terms endothermic and exothermic. Endothermic means energy is coming into the system. So boiling, we put energy into the liquid, so it's an endothermic process. Freezing is exothermic, because as we are cooling off the liquid, we are removing heat from it, so heat is exiting the system, and that's exothermic. Evaporation, you're going from a liquid to a gas, actually should be endothermic as well. I have a typo there, so it's not exothermic. Physical changes of state, we've got a nice picture from your textbook looking at all the things that you could do: condensing, evaporating, subliming, freezing, and melting, and whether they're endothermic or exothermic. When heat is absorbed, obviously that's endothermic. When heat is released, it's exothermic. There are intermolecular attractive forces between your molecules. They're based on the polarity of the molecule. And there's 3 different types that we're going to talk about. London, which occurs between 2 nonpolar molecules. Dipole-dipole, which occurs between 2 polar molecules. And hydrogen bonding, which the name is a little confusing here because intermolecular attractive forces are not bonds. Bonds are within the molecule, they're very strong. Intermolecular attractive forces are between 2 molecules, and they're pretty weak. But this last one is called hydrogen bonding because it's between molecules containing NH, FH, or OH bonds, and that particular interaction is called a hydrogen bond. So in hydrogen bonding, we can look at this top example here with hydrogen fluoride and see that your interaction is really the hydrogen interacting with the lone pair of electrons on one of the adjacent fluorines. And the reason this happens is if you think about this particular bond between fluorine and hydrogen, we know that it's really polar because fluorine is one of the most, well, it is the most electronegative element on the periodic table. So that means this bond is kind of a superpolar bond. And the hydrogen is has a very large partial positive character. So it's all ready to interact with the long bonding pairs of electrons sitting on the fluorine. We see a similar thing here between hydrogens bonded to nitrogens and an adjacent ammonia molecule that has a non-bonding pair of electrons as well. Dipole-dipole, like I said, exists between 2 polar molecules. And you can see here, here's a polar molecule. Its negative ends are interacting with the positive end of another molecule. And its positive end is interacting with the negative end of another molecule. It's pretty much like thinking about a whole bunch of magnets running around. Which ends do they interact with? How do they interact with them? In London, you have nonpolar molecules. So these molecules here, molecule A and molecule B, they're nonpolar. They've got an equal distribution of electron density. Something called an instantaneous dipole can occur on molecule A. And what happens there is, if you think about it, your electrons are constantly in motion. And we can talk about the probability of where they might be, like we did in Chapter 3. And there is some probability that at some point in time, all the electrons will be on one side of the molecule. When that happens, you get what's called an instantaneous dipole. So my nonpolar molecule now starts to build up partial positive and partial negative charge. Well, then molecule B looks at that and says, whoa, and moves its electrons towards the partial positive on A. So we get an instantaneous dipole that's induced. Now, this does not last long, and it's not very strong as an intermolecular attractive force. In fact, London forces are our weakest intermolecular attractive force. Because as soon as these molecules move away from each other, the electrons will go back to their lowest energy state, which is the nonpolar equal distribution of electrons around the molecule. So one of the questions that you're going to be faced with asking in your homework and on quizzes is, what are the intermolecular attractive forces present in each of the following molecules? And the questions you want to ask yourself are, is it polar? Is it nonpolar? Does it have NH, FH, or OH bonds? So let's look at NH3. When we draw its Lewis dot structure, which is a good idea to do on these, we see that we have 3 NH bonds. Because we have NH bonds, we know that the intermolecular attractive force between ammonia molecules is hydrogen bonding. CHF3, when we draw the Lewis dot structure, it looks like this. It was important to draw the Lewis dot structure, particularly on this one, because if you didn't, you might have thought that the H and the F's were bonded together, but they're not. They're all bonded to the central atom, which is carbon. Since that's the case, there is no HF, OH, or NH bonds within this molecule, which means that hydrogen bonding is not an option. So then we have to evaluate, is this molecule polar or nonpolar? When we look at it, we see that it's not symmetrical. It's got 3 fluorines and 1 hydrogen. So it doesn't have all the same things around it, which means that it's polar. Because it's polar, all polar molecules, which don't have NH, FH, or OH bonds, have dipole-dipole intermolecular attractive forces. CH4, when we draw its Lewis dot structure, has 4 H's. It's symmetrical. We know it's nonpolar, which means that we can automatically conclude that it has London forces for its intermolecular attractive forces. How then do intermolecular attractive forces affect your physical properties? And specifically, boiling points and freezing points. So let's start with boiling. If you think about it, when you boil something, you have molecules that are pretty close together, right, in the liquid state. And when you boil, you're asking those molecules to move farther apart. So whatever intermolecular attractive force there is between molecules, we have to put enough energy in to overcome them to force them to be apart over here. So that means if I have high intermolecular attractive forces, then the molecules really like each other, which means I have to put a lot of energy in to force them to be separated. That results in a high boiling point. Should have had a P in there. On the other hand, if I have really weak intermolecular attractive forces, then I don't have to put very much energy in to boil to separate those particles, and therefore I would have a really low boiling point. When it comes to freezing points, in this case, what we're asking is, say I have a molecule that freezes at 50 degrees and another molecule that freezes at 30 degrees. So 50 degrees is a higher freezing point than 30 degrees, right? If you think about it, when you're freezing something, you're removing energy. You are slowing the particles down enough so that they will interact with one another and form a solid. So in freezing, we have particles that were kind of close together in a liquid, but now we're asking them to be really close together in a solid. And so we're removing energy from the system so that they'll slow down enough and interact enough to form the solid. So if something has high attractive forces, then I probably don't have to remove very much energy to get them to interact with one another. On the other hand, if something has weak intermolecular attractive forces, I have to remove a lot of energy, which would result in a low freezing point in order to get a solid. So high intermolecular attractive forces will give me high freezing points. And weak intermolecular attractive forces will give me low freezing points. And you can take this and apply it to all the different changes in physical state that we talked about. Just thinking about it in the sense of, are you bringing particles closer together and removing energy to do that? Or are you forcing them to be farther apart and putting energy in to do that? Vapor pressure is another physical property that's impacted by intermolecular attractive forces. This is the pressure from evaporated liquid in a closed container. Let's see if I have a picture. Nope, so I'll draw one. So if you imagine a container that has some liquid in it, it turns out at the surface of the liquid there are particles. And over time, if the container's closed, here's my lid, the particles jump into the gas phase. And eventually you get a certain number of particles in the gas phase, and an equilibrium develops where particles are jumping out of the liquid phase and back into the liquid phase at an equal rate. The number of particles that I end up with in the gas phase are going to give me that vapor pressure. So then the question is, who's going to have a high vapor pressure? A pair of molecules with strong intermolecular attractive forces or weak intermolecular attractive forces? Take a moment and think about that. Okay, if you think about it, in order for molecules to get into the gas phase, they have to leave their neighbor. So if they feel very strongly attracted to their neighbor, then how many molecules will make it into the gas phase? Well, probably not very many, which means that if I have high intermolecular attractive forces, then I won't have very many molecules in the gas phase, which means I will have a low vapor pressure. On the other hand, if I have weak intermolecular attractive forces, then the particles are kind of so-so about each other and quite eager to jump into the gas phase, which means I'll have a high vapor pressure. Let's look at some examples. Does CCl4 or CH3Cl have a higher boiling point, lower freezing point, or lower vapor pressure? So go ahead and hit pause and think about those for a few moments, and then when you're ready, start this back up again. So the first thing you want to do is draw your Lewis dot structure and decide what intermolecular attractive forces these have. So CCl4 has 4 chlorines bonded to a carbon, and CH3Cl has 3 hydrogens and 1 chlorine bonded to a carbon. And we can see that CCl4 is a symmetrical molecule. It is therefore nonpolar. All nonpolar molecules have London forces, which are the weakest of the 3 forces, as their intermolecular attractive forces. CH3Cl is not symmetrical, which means it's polar, and it doesn't have NH, FH, or OH bonds, which means it can't be hydrogen bonding. So I'm left with this as being dipole, because it's a polar molecule. Dipole forces are stronger than London forces. Hydrogen bonding are the strongest of the 3. So let's now use this information to figure out the answers to the question. Highest boiling point is going to come from the molecule with the highest intermolecular attractive forces. CH3Cl has dipole-dipole intermolecular attractive forces, which are stronger than London forces. So therefore, the higher boiling point will come from CH3Cl. The lower freezing point will come from the molecule with lower intermolecular attractive forces, because we'll have to cool it a lot to get them to slow down and interact with one another. My weaker intermolecular attractive forces come here from the London molecule, or CCl4. The lower vapor pressure, remember we just talked about this, the stronger intermolecular attractive forces mean that my particles at the surface of the liquid are not going to jump into the gas phase very readily, which means that they'll give me a lower vapor pressure. So my dipole-dipole molecule with its stronger intermolecular attractive forces gives me a lower vapor pressure. Hopefully you got all of those right. And that's it for Chapter 7. Your homework is number 7 through number 68 in the end of the chapter problems, which start on page 187 at the end of Chapter 7.